Hello friend, I am Ghanashyam and welcome all of you to the electric neuron. Today we are going to discuss the problem on power system analysis. That is our part number 3. We have already discussed the part number 2 in the previous lecture. So let's start our video lecture. So question number 1 is saying that consider a long wire of transmission line composite of solid ground conductor. The radius of the both conductor is 0.25. So I am saying you here that conductor 1 and conductor 2 have the radius 0.25 and the distance between their center x meter. So from center of 1 and center of 2 the distance is x meter. If the distance is double, then the inductance per unit length is what? So it is asking about when the doubling of that x meter, then what will the effect on the per unit length inductance. So here in this question the x means that d, distance. So we have already know the inductance formula, that is directly proportional to ln d divided by r dash. D is your the distance and the r is your radius. From the inductance 1, that is equal to directly proportional to ln d divided by r dash. Now we are increasing the distance, that is 2d, that is equal to ln 2d divided by r dash. So here it is directly proportional to, so it is increasing but not double in nature. Why? Because of it is in logarithmic in term. Because of it is in logarithmic in term, that why it is logarithmic increase, but it is not double simultaneously. Okay, so this is your answer of the question number 1. So let's come to question number 2. Question number 2 is saying that a one phase conductor of diameter 4 cm is carrying 30 ampere of current. So see here, this is your conductor, the diameter is 4 cm and radius is 4 divided by 2, that is equal to 2 cm. And from the surface of the conductor to the point of P, there is 3 cm distance. In the figure this, the ratio of the external flux linkage to the internal flux linkage up to point is, so it is asking about to finding external flux linkage to the internal flux linkage. So for external flux linkage we have one formula, that is equal to mu 0 I divided by 2 pi ln d divided by r, or the unit is Weber turn per meter. For internal flux linkage, that is equal to mu 0 I divided by 8 pi. Instead of 2 pi we are using 8 pi, because if multiply here 4, then you will get 8 pi, and we are not using these terms ln d divided by r in the internal flux linkage, and the unit is Weber turn per meter. So the diameter is given only, there is 4 cm, and the radius diameter divided by 2, that is equal to 2 cm, and current is given 30 ampere. And the distance from the center of the conductor to the point P, that is equal to 3 cm, and the center radius, that is 2 cm. So adding this both term, then you will get 5 cm. So after dividing these two equation, that means the external flux linkage divided by internal flux linkage, then we will cancel these terms. First mu 0 I divided by 2 pi here, and mu 0 I divided by 2 pi, and the only left term is 4 ln d divided by r divided by here 1, only 1 is left. So this is here external flux linkage divided by internal flux linkage. After calculating this and putting the distance value d, that is equal to 5 cm, and radius value r, that is equal to 2 cm, divided by 1, then we will get 3.6652. So this is your answer from this. Okay, let's come to the question number 3. Question number 3 is saying that a standard conductor having the 7 identical conductor, this is your standard 7 identical conductor, each have radius up to 2.3 millimeter, is shown in the figure this. find the ratio of the self GMD to overall outer radius of the conductor. So first we need to calculate the self GMD, then overall outer radius of the conductor. So for self GMD we need self distance that is from 1 conductor, from 2 conductor, from 3 conductor, from 4, 5, 6, 7, like that. So for D11 that is 0.7788 r. For D1 to 2 and 1 to 7, 1 and 1 to 6, the distance is same, that's why we are equaling all the terms, that is equal to 2r. From conductor 1 that is r radius, for conductor 2 r radius, so adding both the radius then you will form 2r, like that for the all this conductor from center to center spacing, like that. D24 is equal to 4r, D13, D15 that is equal to this. You have to solve this by applying this Pythagoras theorem here, then you will get this term that is equal to 3.4641 r, like that. It is self 1, self 2, self 3, self 4, self 5, self 6, that is equal to this for self radius and the mutual radius, this, like that. The 7 term come here, that's why where the power here 1 by 7. So after calculating this you will get 2.3577 r, like that. D57 that is equal to this 5.0062, not 5.0062, sorry, and that is equal to these terms 1.7479. After putting all those value in here self GMD, then you will get 5.0062. So now overall the outer radius that is equal to r flow from here and 2r from here, so that is equal to 3r. After putting the value of r that is equal to 2.3 millimeter, then you will get 6.9. So the ratio of self GMD to the outer radius of the conductor, so self GMD is here 5.0062 to put here, and the outer radius that is equal to 6.9. After calculating or dividing this, then you will form 0.7255. So now come to the question number 4. Question number 4 is asking that each strand in the bundle conductor shown in the figure 3.1 and 3.2 has a radius of r1 and radius of r2 respectively. If the self GMD of the conductor configuration shown in figure 3.2 is greater than or not is half than that of the bundle conductor of configuration shown in the figure 1, then find the r1 divided by r2. So for r1, r2 we need to find the self GMD first, and here the self GMD are equal in the both the case. So first we need to calculate the self GMD of the conductor of this figure and self GMD of this figure. So for self GMD we need first D1 that is equal to 0.7788 R1, D2 D3 is equal to 2R, this is your D2 and this is your D3 is equal to 2R, and in this case the D1 is equal to 0.7788 R1 and D2 D3 is equal to, this is your D2 and this is your D3, that is equal to 2R2, and D4 is equal to, by applying the Pythagoras theorem here, hypotenuse square is equal to b square plus b square, then you will form these terms. D4 is equal to 2.88 R2. For self GMD of the this figure, this is 1.460 for R. For self GMD of this figure, that is 1.7228 R2. So equaling this term, then you will form R1 divided by R2 is equal to 2.3593. Now come to the question number 5. In a 3-phase 50 Hz transmission line consisting of 3 equal conductor of radius R1 placed in a horizontal plane within a spacing of 7 meter distance from center to center, from A, B, C, here 7 meter distance from A to B, B to C, and the and it is asking about finding the determine to determine the inductance, that is millihenry per kilometer in terms per phase of the transposed line. If the diameter of each conductor is 1 centimeter, then radius is equal to 1 by 2, that is 0.5 centimeter, and spacing between two outer conductors, that is equal to 7 meter plus 7 meter is equal to 14 meter, and the spacing between two central of outer conductors, that is equal to 7 meter here and 7 meter here. So the mutual GMD of the conductor, that is equal to 7 into 7 into 14, that is to the power 1 by 3, that is equal to 8.8194, and the self GMD of the conductor is equal to ds is equal to 0.7788 r for the conductor Y, conductor B and conductor C, that is equal to this, and putting here r value, then you will get the term self GMD is equal to 3.894 into 10 to the power minus 3 meter, and inductance of the conductor, that is equal to, we have already know the formula, 2 into 10 to the power minus 7 ln dm divided by ds, or d mutual divided by d self. Then put here the mutual value and put here the self value in this equation, then you will form 1.5450 millihenry per kilometer. So this is your answer for today. That's it. Thank you for watching. See you in the next lecture.